Hi, and welcome to 16.2 Particle Wave Duality and Photon Energy. There's a lot of really cool concepts packed into this topic. However, for this video, I'm really just going to show you how to utilize the reference table and where I'm pulling all this information from. I guess we could start there. I'll show you the main parts of the reference table that we're going to use for this lesson. So if you already tried this and you kind of got lost, maybe this will be some good hints for you, right? So the 1 electron volt is equal to this many joules, 1.6 times 10 to the negative 19 joules. That's going to be important to know. Planck's constant, H, is right here for you. We're going to need that for some of the equations. And I think on this page, those are the two that we're going to need for this lesson. Yes, I think in the last video I said, oh, this is all just unit 15. Oh no, it actually does come up again here. We're going to need to use this, specifically looking at the frequency and the powers of 10 for the answers that we're going to get for the frequency to determine what type of electromagnetic radiation these different photons are. Okay, we're not going to really talk about refraction. And then we're not there yet. We're not going to do this one yet. That's the next lesson. We did this one in 16.1, so we're not going to need that for this lesson. Let's go down to the modern physics. So we're going to be dealing primarily with this equation here. Okay. And, we could talk about the units, I guess, quick. So, well, I don't know. It's worth noting that for this energy, it's in joules. For this energy we'll be using today, we'll use joules. And then this we didn't really do yet, but this is in electron volts for this equation specifically, because this equation is referencing this table here, where the energy is in electron volts, and you're going to have a difference between the energy levels. That's what that EI minus EF is all about, just so you know. But for the other two equations that have to do with the energy, it's going to be in joules. And for this, it's for the reason that it's in joules is because Planck's constant is in terms of joules on the front of the reference table. So if you look here, we want to make sure our units agree with the joule second, not an electron volt second. If you have the version of Planck's constant that is in terms of electron volt seconds, it's a different number, then you would use electron volts for the energy. Anyway, so that's like an overview of what we need to know about the reference table to do these problems. Try them out on your own first before I go over them. Number 1 says a monochromatic beam of light has a frequency of 7.69 times 10 to the 14 hertz. So they're telling you the frequency. And they ask, what is the energy of a photon of this light in joules and electron volts? So they're looking for the energy. That's not going to be enough information here. We need to know something else. And we always know Planck's constant, H. All right, so let's look at the reference table. Planck's constant is 6.63 times 10 to the negative 34 joule seconds. 6.63 times 10 to the negative 34 joule seconds. All right, so here's our givens and our unknown. Which equation are we going to use? Well, they give you the frequency, and we always know H, and they're asking for the energy, so we're going to use E is equal to HF. And then just like always, you substitute in your values and you get 5.098, so 5.1 times 10 to the negative 19. And then if we wanted to take a look at our units, we have a joule times a second times a hertz. Okay, so a joule times seconds times hertz. Well, if you remember, hertz is the unit for frequency. How frequently the wave passes, how many cycles per second. So cycles per second. Hertz is really just an inverse second, or second to the negative 1 power. And that's why these seconds cancel out. And that's why it's important that we remember that if you're using this formula with this version of Planck's constant in terms of joule seconds, we're going to get an answer in terms of joules, which is the first thing that they ask for. Then they also ask, hey, tell me the energy in terms of electron volts as well, which we can also do. So we have our answer in terms of joules. We just need to know what the conversion factor is. And here we go. They tell you 1 electron volt is equal to a very tiny amount of joules, right? Because when we're talking about this modern physics, quantum physics, all this stuff, if we just left everything in terms of joules, it would always be like a tiny number. Not always, but like it's helpful to have a unit of energy that, takes that into account. So we'll use that. So we've been converting units since the very first unit. You just write the number down with its units, please. Then you multiply by some parentheses. You put a line in the middle. Don't make it a distraction because we're about to use a really cool fraction. Write the unit that you just wrote on the opposite side so that they cancel out, leaving you with pride. Write the unit that you want in the only blank space. And now we're ready for some numbers to take their place. How many of one thing equals the other? That's the question we've been asking for a very long time. I won't go through the rest of it, but let's see. The reference table says 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, right? So that's how you set it up. You don't have to guess on where to put this number. Do I multiply? Do I divide? It's just converting, so if you've been practicing this method, this should not be so bad. You end up getting 3.1865, we'll call it 3.19 electron volts. Nice. All right, number 2. Now they're telling you the amount of energy. A photon has 1.66 times 10 to the negative 23 joules of energy. See, that's a very tiny amount of joules. Part A says, put that in electron volts, please. So you write the number down, its units, and then you just multiply by your conversion factor so that the units cancel out. The joules go on the bottom because the joules were on the top before. And now we're ready for the numbers to take their place. The reference table says 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. All right, just so that you see it again. And you get a small amount of electron volts, 1.04 times 10 to the negative 4 electron volts. So that's for part A. Part B says, what is the frequency of this electromagnetic radiation? That's what EM stands for. All right, so if we know the energy and we're going to use it in terms of joules, we could write down the given information. A little bit of a side, they're trying to trick you. Oh, do I use the electron volts? No, because Planck's constant is in terms of joule seconds, at least the one they give you in the reference table. And they're looking for the frequency. So we'll use the same formula we used before. E is equal to HF. If you want, you could solve for the frequency first. F is equal to the energy divided by Planck's constant, which is equal to that many joules divided by that many joule seconds. And you get a frequency of 2.5 times 10 to the 10. And then what are the units for frequency? We know it's hertz, but does it work out? Yeah, joules cancel with joules, leaving you with 1 over second. An inverse second is known as a hertz. Cool, 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 cool. So that is the frequency that we're looking for. 2.5 times 10 to the 10 hertz. Part C says, what kind of radiation might this photon be? All right, remember, photon is an electromagnetic, it's electromagnetic. So we could look at the electromagnetic spectrum, and we're looking for a frequency 10 to the 10. So we're flipping all around the reference table for this unit. So you have to be really nimble on your feet here, okay? So we had a frequency of 10 to the 10, 2.5 times 10 to the 10. And then it looks like, oh, is it radio waves or microwaves? Yeah, that's true. All right, but this was 2.5 times 10 to the 10, not like 1 times 10 to the 10. That would be right here. 2.5, is that to the left or to the right of that? Well, 2.5 is bigger than 1, right? So this is going larger to the left. So 2.5 would be somewhere around here, which is a microwave, not a radio wave, okay? I could see why you would say maybe radio wave, because it's oh, it's right there. But it's 2.5 times 10 to the 10, so it's a little bit greater than that, right? See how that works? Cool. But we're talking about a microwave here with that type of frequency. All right, number 3, a monochromatic. That just means one color. A monochromatic beam of light has a wavelength of 4.3 times 10 to the negative 12 meters in a vacuum. What is the frequency of this radiation? What is the energy of a photon of this radiation in joules and electron volts? And what kind of radiation might this be? So hopefully you can, if you didn't try this yet, try this one out on your own first before I do it, because I'm going to do it kind of quick now. Part A is a little bit different. So now they're telling you the wavelength, right? So lambda is equal to 4.3 times 10 to the negative 12 meters. And what we always know, H is equal to 6.63 times 10 to the negative 34 joule seconds. What are they asking for? The frequency here. Okay. Yeah, we could, it is tempting to use, like they say, the energy of the photon is equal to HF, which is equal to HC over lambda. Okay. What are they asking for? The frequency, right? Yeah, so I mean, we could use something like this. HF is equal to HC over lambda. That's cool. The H's will cancel out. You're left with F is equal to C over lambda. And then actually, if you cross multiply, you get the wave speed equation. C is equal to F lambda, which is right over here. This is still like a valid thing, right? Because photons are both particles and waves, particle-wave duality. So we can still use this idea. It's just that we have to remember, if it's electromagnetic wave in a vacuum, we already know the velocity of the wave. It's c, the speed of light in a vacuum. Okay, so either way, I probably wouldn't use the modern physics formulas for this one. If they tell you the wavelength and the speed, and they're asking for the frequency, you could just use the wave speed equation. So yeah, this is also a constant that we know, 3 times 10 to the 8 meters per second. All right, so get this mess out of here. Modern physics is cool, but sometimes it's easier to just do this. V is equal to F lambda in the special case that we're talking about electromagnetic wave in a vacuum. So we use C. So if we wanted to solve for the frequency, yeah, F is equal to C over lambda. Either way, it's kind of like semantics, but I wanted to show you the different ways over the wavelength. So 4.3 times 10 to the negative 12. And we might as well do nice thing there. All right, so the meters will cancel out and you're left with a 1 over a second and a frequency of 6.98 times 10 to the 19 inverse seconds or hertz. Cool. All right, so B says, what is the energy of a photon of this electromagnetic radiation in joules and electron volts? Well, now that we know what the frequency is and the wavelength, we could actually use either one of those formulas. I'll probably just use this one because this number is already in my calculator. I just need to multiply it by H. And when you do that, you get 4.63 times 10 to the negative 14 joules, which we can easily convert by multiplying by our conversion factor. Remember, you want the units to cancel. And you get 2.89 times 10 to the 5th electron volts. Okay, so part C, I happen to like part C, those types of questions. So it says, what kind of electromagnetic radiation might this photon be? Remember, we're looking at the frequency. So we got 10 to the 19 hertz as our power of 10 for the frequency. Let's look at our table. So again, frequency 10 to the 19. Oh, that's around here. Okay. So it could either be gamma rays or X-rays because that whole band of 10 to the 19, those fall into both. So we don't know. It could be both X-rays or gamma rays. Very good. So that's how you use the reference table for those types of problems. It's a lot of flipping around. We're using a lot of different pages now. Remember mechanics when it was all basically just the last page? Yeah, cool. Number 4, which graph best represents the relationship between photon energy and photon frequency? What does the slope of this graph represent? Oh, 2 different problems. Did you answer the second question too? I don't know. All right, so photon energy is E. Photon frequency is F. And it's what is the relationship? So we need an equation that relates E and F. You look in your reference table and at most of the problems that we've done so far, and we know that E is equal to H times F, not HF squared, not H over F, not H over F squared, but H times F. So how are frequency and energy related? They are directly related. So what would we expect the graph to look like? Choice B, it's a direct relationship between the frequency and the energy. All right, and then what does the slope of the graph represent? Well, slope is just rise over run, right? The photon energy over the frequency. So let's manipulate our formula so that we have rise over run, energy divided by frequency, like so. And we see that Planck's constant is equal to the energy divided by the frequency. So we know the slope is equal to h, which is equal to 6.63 times 10 to the negative 34 joule seconds. Nice. And then number 5, nice and easy to round it off. Light demonstrates the characteristics of both particles and waves. Particle-wave duality for light. Cool, very good. Anyway, that's about it. Have a great day. Thanks for watching.